Okay. Okay.
Hi,
So
Alf.
welcome. Everything is okay, right? Welcome everyone. Everyone. Today I have the pleasure to introduce Kerstin Jordaan, who is a full professor in the University of South Africa, and she is very well known in the orthogonal polynomial community. And his area of interest is the integrable systems, of course, special functions, orthogonal polynomials, asymptotic analysis. And today, she will talk about generalized higher order Freud weights. Kerstin, thank you very much for accepting our invitation, and you can start whenever you want.
All right. Thank you very much for the invitation to speak. So in this talk, which is based on joint work with Peter Clarkson and Anna Loureiro, um, both from the University of Kent, I will consider generalized higher order Freud weights for m equal to 2, 3, 4, etc., as defined over here. I will give closed form expression for the moments with respect to the weight, and also investigate recurrence coefficients in the three-term recurrence relation and their asymptotics. Then I will review a method based on a characterization of semi-classical orthogonal polynomials that gives nonlinear relations satisfied by these recurrence coefficients. I will also prove mixed recurrence relations satisfied by these generalized higher order Freud polynomials. And finally, I will consider the zeros. The limiting distribution of the zeros is determined by the asymptotic behavior of the recurrence coefficients. And I will also present some other properties of the zeros. So to start with some of the earlier history, in 1976, Freud considered orthogonal polynomials with respect to the weight, where there's also an algebraic term like this, like I had in my weight, and it's e to the minus x to the power of 2m, but the plus t x squared term is missing, so the semi-classical perturbation is not in this weight. And he considered these weights for lambda greater than -1 and m going from 1, 2, 3, etc. He showed that they satisfy the three-term recurrence relation in this form, and gave the recurrence relation for beta n in the cases when m is 1, 2, and 3. So when m is 1, he showed that the recurrence coefficients satisfy this equation over here, and that is exactly the same expression as what we have for beta n when we look at lambda equal to -1/2, so that this term vanishes, then beta n is n over 2. That's the same as in the Hermite polynomial case. Then when m equal 2, he showed that the recurrence coefficients satisfy this nonlinear equation, which is a special case of discrete Pandavay 1. And in the case when m is 3, he showed that they've satisfied this more complicated expression. And this is, in fact, a fourth order nonlinear discrete equation, which is a special case of the second member of the discrete Pandavay 1 hierarchy. So this connection between the Pandavay equations and the recurrence coefficients goes back quite a lot further. Specifically, the relationship between semi-classical orthogonal polynomials and integral equations dates back to Shohat, who introduced semi-classical orthogonal polynomials as natural generalizations of classical orthogonal polynomials. Moroni proved a unified theory for these semi-classical orthogonal polynomials. So what do I mean by semi-classical orthogonal polynomials? Well, one way to characterize them is by looking at the form of the Pearson equation. So we know that classical orthogonal polynomials satisfy a Pearson equation of this form, which is a first order derivative, a differential equation, where sigma x is a monic polynomial of degree at most 2, and tau x is a polynomial with degree 1. For semi-classical orthogonal polynomials, the weight still satisfies this type of equation. But in this case, either the degree of sigma will be more than 2, or the degree of tau will not be equal to 1. And also, the sigma and tau that appear in the Pearson equation will not be the same as in the second-order differential equation satisfied by the polynomials, as is the case in the classical case. So let me review some of the theory of orthogonal polynomials, but specifically focusing on symmetric weights. So I'm looking at a weight like this. So it's positive on the real line, for which all the moments exist. And then the corresponding monic orthogonal polynomial sequence is given, satisfies this orthogonality relation. And we know that these orthogonal polynomials satisfy a 3-term recurrence relation of this form when the weight is not symmetric, where the recurrence coefficients alpha n and beta n are given by these integral equations. So when the weight is symmetric, or wx equals w minus x, it follows immediately that this integral, because it's on the whole real line and it's an odd function that we're differentiating or integrating, it follows that this integral will be 0. So we're only left with a beta n. At the same time, the monic orthogonal polynomials satisfying or associated with such a symmetric weight are also symmetric in the sense that Pn of minus x can be written as minus n 1 to the n times Pn of x. And this implies that each Pn contains only even or only odd powers of x. And so we can write P of 2n in this form. And remember, I'm looking at the monic case, so the leading coefficient is 1. So it's x to the 2n plus some coefficient for x to the 2n minus 2, continuing like that up to the constant term. And in the odd case, we again have x to the 2n plus 1 with monic leading coefficient of 1. And then all the odd powers, meaning that the last term in the expression is x. And this means that we can factor out an x here. And so we always have a 0 at the origin for these polynomials. And so once we have these expressions, if we substitute them back into the recurrence relation and compare the coefficients on each side, we quite readily obtain that these straightforward expressions which hold for any orthogonal polynomial with an even weight or symmetric weight, that beta to the 2n can be expressed as the second coefficient in the expression of P2n minus the second coefficient for the odd polynomial of degree 2n plus 1. Whereas beta 2n plus 1 can be written in terms of a ratio of these two constants, c naught 2n over 2n plus 2 over c naught 2n and the negative of that, which just means it's the constants of the polynomials evaluated at 0. So I will need these expressions later on, which is why I specified them here. Oh, sorry, I mean to go down. Okay. So furthermore, for symmetric weights, the odd moments vanish because, again, you're integrating an odd function over a symmetric interval, and hence it is possible to write the Hankel determinant. All the even moments will be 0, or the odd moments will be 0. So this determinant can be simplified, it can be written, it can be decomposed into a product of two simpler Hankel determinants. And we can find this composition quite easily by matrix manipulation, interchanging columns and rows. So the product decomposition depends on whether n is even or odd. And So in the even case, it's AN, BN, where AN is this determinant, and BN is just the determinant shifted one on. So the first row deleted, but another row added at the end. So once we have this product decomposition of the Hankel determinants for the odd and the even case is just, as you can see, quite similar to the odd, but it's not exactly the same. Then we can show that for a symmetric weight, any symmetric weight, because the recurrence coefficient has this well-known expression in terms of the ratio of Hankel determinants like this, we can write the even ones and the odd ones now as ratios of simpler Hankel determinants. Oh, I'm going the wrong way again. All right, so I will consider polynomials orthogonal with respect to the generalized higher order Freud weight in this talk, and I'm aiming to bring a comprehensive self-contained analysis of these polynomials when the parameter m takes integer values higher than 1, and for any values of lambda greater than -1 and t a real parameter. The analysis for the particular cases of m2 and 3 was first considered in the first 4 papers, which are listed here. So for M2 here and M3 there. So this is a generalization of the classical Freud weight in the sense that we have the semi-classical perturbation of plus dx squared. The latest paper listed at the bottom here with Peter and Anna, we extended existing theory on Freud type weights to higher orders of M, so M4, etc., providing a coherent and consistent approach. And we attempted to use techniques which can be adapted easily to study other semi-classical type weights. Just one last comment is that this generalized higher order Freud weight that I have over here is indeed symmetric. And it is a semi-classical weight because it satisfies a Pearson equation with sigma x equal to x and tau x a quadratic, so it's not of degree 1. And therefore, it's semi-classical. Right, so I'm going to start by giving a closed form expression for the moments. But first, I should just mention that the existence of the first moment associated with this weight follows from the fact that at infinity, the integrand behaves like e to the minus x 2m, and at x equal to 0, the integrand behaves like x to the rho, the algebraic part with rho equal to greater than -1, which also is integrable. If I look at the even moments, they can be written in terms of derivatives of the first moment by just looking at the expression in terms of integrals and then swapping, noticing that we actually have a derivative over here, a kth derivative of the expression here. And the interchange of integration and differentiation is justified by Lebesgue's dominated convergence theorem. And then just simplifying this expression, we get that the even moments can be written, so a moment of for the degree 2k case can be written as the kth derivative of the first moment. And I'm specifying here lambda and m, specifically because we have another expression for the even moments, which also follows straight or immediately from the definition. If you look at this expression here, you can just see it as the first moment of where lambda has been shifted by k. So we have 2 expressions for the even moments, which we'll use in the work to follows. And obviously the odd moments vanish, as mentioned before. The point of all this, I think, that I should stress is that the first moment is very important. Once you know the first moment, you actually know all of the moments. So what can we say about the first moments? Well, we have the following closed form expression for the first moments. It's given in terms of sum of M terms, where the terms in the series expansion are actually hypergeometric functions. 2fm hypergeometric functions, but if you look at this expression over here quite carefully, you'll see that in the denominator parameters, we have k over m, k plus 1 over m. So one of these terms will be m over m, which means that it will cancel with this 1 in the numerator parameter. And so actually what this is a 1fm minus 1. So we have a linear combination of 1fm minus 1s with coefficients given by gammas, and we have these t to the power of k terms as well. The reason for writing it in terms of a 2fm is just that that gives a much more concise expression. So furthermore, we can see that the first moment satisfies this mth order differential equation. And once we have a differential equation, of course, of this form, it is often much easier to derive properties of a function from this type of differential equation, especially because working with a sum of hypergeometric functions like this is not necessarily easy. So in some cases, it's easier to work with a differential equation. But what this shows quite clearly is that since the sequence of generalized higher order Freud weights for m going from 2, 3, 4, etc., forms a hierarchy of weights, one obtains associated hierarchies for the first moment, and as a result, also for the recurrence coefficients, as I'll illustrate next. So for the generalized Desic Freud weight, I just want to show this to illustrate the previous page for a specific example. So this is the case where m is 5. You can see that the first moment is this sum of 5 1f4 hypergeometric functions where there's a definite pattern which allows us to give the closed form, which we've proven formally, analytically. So, and the 1f4 satisfy generalized and fifth order ODE, and so we get this expression that mu naught satisfies. So what I'm going to do next is look at the recurrence coefficients. I've got to move. Right. So first of all, this expression here for my determinants of moments, the simplified Hankel determinants, can be found in textbooks of determinants, and it's satisfied, this type of expression is satisfied by determinants of that specific form. So it's an plus 1 bn is bn minus 1 can be written as an over the derivative, an times the derivative of bn with respect to this parameter t minus bn times the derivative of an with respect to the parameter t. And so we had this expression for beta for the even moments. And using this, we just plug it into the numerator over there. We can write the even recurrence coefficients as logarithmic derivatives of the ratio of bn over an. And this we can simplify even more. It's the logarithmic derivative of ant if, for the parameter lambda plus 1 over an. And that we can see quite easily from the fact that the moment of the even moment of order 2k plus 2 is the even moment of 2k with lambda shifted by 1. So looking carefully at an, it means, and bn, it means that you can express bn as just an for the parameter of lambda plus 1, because mu naught or mu2 is mu naught of t lambda plus 1, etc. So that's how we get this expression. Now, what I also just want to point out before I show the next slide is that this an, that so we've got the even recurrence coefficients written in terms of this Hankel determinant AN. And this AN is actually just a Wronskian of the first moment, because all of these are derivatives of the first moments. The second row is a derivative of the first row, etc. So each of these rows in the determinant is a derivative of the kth derivative of the, or at least this is the kth derivative of the first row. So we have Wronskians of Hankel determinants, and that allows us to write now, in summary, what we know about these generalized higher order Freud weights. So we know that the associate monic polynomials satisfy this recurrence relation given over here. And beta 2n, we showed on the previous slide how we can get this. We can do something similar for the odd recurrence coefficients, and this AN is just this Wronskian of the first moment. And the first moment, we have a closed form expression for it. So we can generate the polynomials and the recurrence coefficients from this. Next, I'm going to look at some of the discrete equations, nonlinear equations satisfied by these recurrence coefficients. And I'm going to follow the approach by Moroni from 1999, which is based on the structure relation of semi-classical orthogonal polynomials to find the nonlinear recursive relations. So for a given m greater than or equal to 1, we can write x to the 2m times pn as a linear combination of polynomials in the orthogonal sequence, L going from minus m to m. And we have an expression for the coefficients in this linear combination given by these integrals. Using this and the recurrence relation and following an iterative process, we end up being able to show that the recurrence coefficient satisfies a discrete equation of this type, where this Vn2m is just simply the, it involves the coefficients in this linear combination and the recurrence coefficients. So equations such as this for recurrence coefficients are sometimes known as Laguerre-Freud equations. And for the case when lambda is equal to minus a half, so when we don't have this term, this proposition was in fact proved by Benassi and Moro in 2020, but they used a different technique. We're using just orthogonal polynomial techniques. So once we have this expression, we can find expressions for this V into M recursively now. So when M equals 1, Vn of 2n just simply is beta n. And Vn of 4 will be Vn2 times this. I'll just show you quickly the formula again. We're just using this and recursively what we know about the semi-classical linear combination for the linear combination for semi-classical orthogonal polynomials. So using these two and then the formula that we obtained on the previous page in our proposition, we can put Vn2m in here, and we get the first, I didn't give the case for m equal to 1, but for m equal to, we have Vm4, and you can see the right-hand side over here, and here we've just put Vn2, which is Bn into this, beta n into this expression, and you can see how you get this. So this is, again, a special case, or no, it's discrete Painlevé 1. And it's exactly the same as the discrete Painlevé 1 that for the Freud weight that Freud obtained, except that in this case now we also have this term minus 2 beta n, which is needed because we had that semi-classical perturbation in our weight. So it's analogous to what Freud obtained. So for m equal to 3, we get V in 6 is this by using an iterative process. It's just a little bit of work to do it, but it's nothing difficult about it. And then plugging that back into this equation, we get this nonlinear discrete equation, which is again the second member of the discrete Pan-Levé-1 hierarchy, and the same as what Freud obtained for the case beta m equal to 3, except that we have this additional term. So these equations were derived by Freud for t equal to 0, and when lambda equals -1/2, they're also known as string equations, and they arise in important physical applications, such as two-dimensional quantum gravity. So a more recent reference for some of this work than Freud's work is Van Asse's book. And I should also just point out that it's straightforward to modify the proof for the case t equal to 0 to the case t non-zero, Freud's type proof. And that was already done by Wang, Zhu, and Chen in 2020. Our method to do this using the theory of orthogonal polynomials gives us just a straightforward method that can also be used for higher orders. So that's the big advantage. So see specifically here the case for when m is 4 and m is 5, we can get the expressions for Vn and then get the expressions for beta n by using these equations. However, I'm not giving the expressions in terms of beta n since they are rather long, and this is just a more concise expression. Okay, so next I'm going to look at asymptotics for the recurrence coefficients as n goes to infinity. So in 1976, if I look again at Freud's weight, so without the semi-classical perturbation, Freud conjectured that the asymptotic behavior of the recurrence coefficients associated with his weight could be described by this expression over here. So the ratio of beta n over the mth root of n squared, of 1 over m, will approach this constant. And Freud stated the conjecture for orthonormal polynomials. I have rewritten it here for the monic case. And he also showed, he proved it for m2, 4, and 6, and he showed the validity whenever the limit on the left-hand side exists. And Magnus proved Freud's conjecture for the case when m is an even integer, positive integer, and also for weights, more general weights, so e to the minus qx, where qx is an even degree polynomial with positive leading coefficients, but he did not have the algebraic term. Then the conjecture was settled in 1986 by Levinsky, Mascon, Saf as a special case of a much more general result for recursion coefficients of exponential weights. So Levinsky and Saf introduced the class of very smooth Freud weights of order alpha, where alpha is positive, and so that associated with each weight in this class, one can define a number, an, which is the unique positive root of this equation, and showed then that for the generalist higher order Freud weight, if you take the Q as in our case, you can then show using Levinsky and Mascon-Saf's result that the limit of beta n over the nth root, or the mth root of n, tends to this constant. And more specifically, for m equal to 2, it means that for this generalized quartic weight, the ratio of beta n over square root n tends to this constant. And for the generalized sextic Freud weight, we get the ratio of this ratio tending towards this constant. So these results were obtained using different proofs in the papers that I mentioned before for the case M2 and 3. but they actually are just special cases of Lubinsky-Maslow result. So I'm just going to look at the exact asymptotics, or more detailed, not just the leading asymptotics for the case when m equals 3. So in the 2021 paper for the case m equal to 3, so this is minus x to the 2m, where m is 3, plus tx squared. We showed that the fourth order linear discrete equation satisfied by the recurrence coefficients is this, which now I've used a different method to obtain it. Then for any weight of this form satisfies this kind of differential equation, also nonlinear, known as the Volterra lattice equation or the Langmuir lattice equation. A proof of this is in Van Asse's book. And using these two, we can follow Magnus's approach. So we're using the Langmuir lattice and the discrete equation in the first bullet to get a system of differential equations satisfied by the recurrence coefficients. And now from this, we can deduce several asymptotics. So first, using the first order linear discrete equation. Oh, I'm going up again. So this is the asymptotics as n goes to infinity. So any recurrence coefficient satisfying this nonlinear discrete equation has the formal asymptotics given below. And as we would have expected, there is a difference between the even and the odd case. So in the case when n is even, we have the leading coefficients as the Freud conjecture gives it to us, and then some more terms in the expansion. And for n odd, the first two terms in the asymptotic expansions, as you can see, is the same, and after that they differ. So it is in the weight, this minus 1 to the n, that expects us to, or that leads us to expect different asymptotic approximations for the even and the odd cases. So I can show the expressions graphically, as I have done here. So we use the expression for the recurrence coefficients in terms of the logarithmic derivative of the matrix of monads, and as well as knowing what the first moment is, and beta 1 just being the logarithmic derivative of the first moment. That enables us to obtain these sketches, which is the blue dots are the even moments, and here I've chosen lambda equal to 10, lambda equal to half and t equal to 10. And the odd moments are given by the red dots. So on this axis, I've just got beta n, and on this axis, I've got the n's. Now, from the plots of the recurrence coefficients as functions of t for different values of n, we see the asymptotic behavior quite clearly. The asymptotics on the previous page are given by the solid lanes, whereas the dashed line is just the first two terms in the asymptotic expansion. So next, I'm going to have a look at what happens as t goes to infinity as opposed to n going to infinity. So for that, I'm going to look at the recurrence coefficients as functions of t. So on this axis now, I'm plotting t, and the different colors in this are the beta n's for n going from 1 for the black, 2 for the red, 3 for the blue, 4 for the green, and 5 for the purple. And again, in these sketches, you can very clearly see the different behavior for n even and n odd. Again, I've taken the simplest case where lambda equals minus a half. So clearly, as t goes to infinity, both in the even and the odd case, we see that for the even case, the beta n's are going to 0, but for the odd case, they're going off to infinity. And but as t goes to negative infinity, they both go to 0. So since the moments involve the sum of three generalized hypergeometric functions, the asymptotics are not as straightforward as for the lower degree cases. Obtaining the asymptotics involved the use of classical asymptotic techniques. In other words, here as t goes to infinity, these are now what I can illustrate with the sketches, but the formal asymptotic expansions. We used Laplace's method to derive the asymptotics for t going to infinity for the even and the odd case. And you can see the different behavior as t goes to infinity for the even and the odd case, the one going to 0, the other one going to infinity. And then as t goes to negative infinity, these are the asymptotic expansions as they both go to 0 as t goes to negative infinity. And this was obtained using Watson's lemma. Oh, come on. All right. So then one last thing, just to the usefulness of these kind of plots of the recurrence coefficients that we can get because we have these expressions of the moments or the recurrence coefficients in terms of the logarithmic derivatives of Wronskians of the first moment. We can conjecture, for instance, that for n odd, the recurrence coefficients are monotonically increasing functions of t, and in the even case, the recurrence coefficients are simply bigger than the previous ones for any t. So one can actually show that these two expressions are equivalent by looking at the Langmuir lattice. So the derivative of the odd ones being positive is the same as this difference being positive. So if you had proved one of these conjectures, you immediately have the other one. But they still are conjectures. We haven't proved them. Then we have a third conjecture that basically these maximum values are increasing as t increases. So they occur for bigger values of t. And also what we can see is that where these maxima occurs is exactly where the odd recurrence coefficients are equal, the consecutive ones. And again, that is obvious from the Langmuir lattice. So when this derivative is 0 and we have a maximum, it means that beta 2n plus 1 would equal beta 2n minus 1. Anyway, that's just to note some interesting conjectures. So what I'm going to look at next is the polynomials themselves. So for m equal to 2 equal to 3, I'm looking at this kind of weight. And now I just want to point out that if I talk about Pn xt lambda plus 1, then I mean the orthogonal, the polynomial orthogonal with respect to the weight with a parameter lambda plus 1, which is just x squared of the original weight. So this boils down to what I'm going to obtain is connection formula between the corresponding sequences of generalized higher order Freud polynomials in the context of Christoffel transformation. So meaning when the weight is modified by a quadratic factor. Or in this case, it's a quadratic factor. For Christoffel polynomials, it can be, or Christoffel transformations, it can be any polynomial factor. So I get this relation between the even polynomial of the, with parameter lambda plus 1 and the odd one with parameter lambda. It's a very simple expression. And this is another expression for relating P2n and P2n minus 1 for 2 P2n minus 1 with a parameter lambda plus 1. And then these expressions basically can be written in a different form by viewing them as connection formulas in the framework of Geronimus transformations, which is just the inverse of a Christoffel transformation. So you view this weight as 1 over x squared of that weight, and then you get these equivalent mixed recurrence relations. So just some plots of the polynomials themselves. For M3, I'm now looking again at just the specific case when M is 3. And these plots are done for T5 and lambda equal to -1/2. And the plot shows the polynomials of degree 3 through to degree 6 in different colors. So what we notice is that in this plot, the zeros are all real and distinct and interlacing. So this property we expect, because even if we have a semi-classical weight, the interlacing and the reality and the distinctness of the zeros, the proof of that in the classical case only uses a 3-term recurrence relation and the definition of orthogonality. So we fully expect to have that hold. What we note as well is the symmetry of the zeros for an even weight, and that in the odd case, we always have the 0 at 0, which I've already explained. Another way to look at the polynomials is to just consider on one plot, the polynomial of a certain degree for different values of t. Then we notice that so it's t naught for black, 1 is red, etc. So we've got black, T2, T3, T4, T5. And what we notice immediately is that all of the zeros, as t increases, increase. And we have the opposing monotonicity because this is a symmetric case for the negative zeros. So the positive zeros increase as t increases. So can we prove this? And the answer is yes. So we can also prove the monotonicity for lambda as it increases. So we use the generalized version of Marcus' monotonicity theorem that holds for polynomials with an even weight. And we got these monotonicity results for this V0. Then we can also obtain an upper bound for the largest zero. That follows by applying a result due to Ismail and Lee, which is based on the Wall-Wetzel theorem, to the 3-term recurrence relations. And notice that this bound is independent of the value of the order of m in the weight. Right. Next, we're going to consider the relative positioning of the zeros. So the figure for the zeros already showed us that we expect interlacing of the zeros of different sequences of generalized higher order Freud polynomials within the sequence. But when we look at different sequences, so this is for the polynomials with respect to the parameter lambda. But if we take another polynomial sequence with parameters lambda plus k, again, m can be of any order. Then we're denoting the positive zeros as follows for the parameter lambda. We have the interlacing results as follows. I know this is a little bit hard to follow from the slide, but this holds for shifting lambda by any k between 0 and 1. So we just have to differentiate between whether our starting zero is even from the even polynomial or from the odd polynomial, because in the one case we have this that xl to n of lambda plus 1 is the same as xl to n plus 1 of lambda, and that follows from this relation over here. So we just have to take that into account. And it is much easier just to see this graphically. So you can see here, this is illustrating the interlacing for P7 lambda, lambda plus 1, and then P8 is again for lambda. You can see the interlacing as what I had it on the previous slide. And in this case, it's not easy to see, but you always have zeros coinciding like I had on the previous slide. And of course, you always have the zero of the odd degree polynomial being at the origin. Right, then, just in closing, the asymptotic behavior of the recurrence coefficients of generalized higher order Freud polynomials, orthogonal with respect to generalized higher order Freud weights, satisfying Freud's conjecture, as we've already shown, is independent of the values of t if you take a fixed t and lambda, and implies that the recurrence coefficients are regularly varying. So to consider the asymptotic zero distribution of generalized higher order Freud polynomials, as n goes to infinity, we can use an appropriate scaling and apply the property of regular variation as was detailed by Kalos and von Asse in 1999. So we get this asymptotic distribution of the zeros given by a 2f1, and we can also specify the interval where the zeros lie. And that density of the zeros can be illustrated by it. So this is that 2f1 function with the appropriate scaling. Okay, so this is where I'm going to stop. I have finished what I wanted to present to you. Thank you very much.
Okay, thank you, Kerstin, for your nice talk. We have time for questions, Edmundo. Edmundo, estás en mute.
Thank you. Yeah. Thank you, Kerstin. Very, very interesting. Yeah, I have a question. Maybe I have two questions. Maybe the first one is a little bit difficult, but okay. Do you know what happens when you consider in the generalized generalizes Freud weights, the m not exactly an integer? I don't know, maybe a rational number. Is it because I think that you have still a positive measure, and maybe these cases could be considered also. You know, instead of have m equal to 2, I don't know, m equal to 2.5 or something like this. Do you know if it is possible to consider this kind of cases?
Well, so it's not really a polynomial anymore, right? That you have, so if you think about what Magnus did, he had e to the minus qx, where q was a polynomial. And what you're proposing is that you no longer have a polynomial in your exponential power.
Yeah, it is. But I think that you also have to, you have a measure, and I think that it should be have a family of orthogonal polynomials with respect to that, even if you don't have a polynomial in the measure, right?
Yes, I have not thought about this. It's a very interesting question. If m is not an integer, I'm noting it down so that I don't forget to think about this. I cannot recall anything that I've seen with these kind of exponential weights without a polynomial in that exponential, or without a polynomial. So you're basically talking about the potential being not a polynomial. Yeah, there must be examples. I haven't thought about that in this context.
Okay, and because indeed, if I'm not wrong, the Freud conjecture is still valid for any m, right?
Yes.
I think that I saw that in your slides.
Yeah.
Yes, but any integer m, I think.
So, in my opinion, there must be something in these gaps, I think.
Yeah.
You know?
It's a very interesting concept.
But I don't know. I don't know. It's just if you know some work or something, it would be great to know. But it's okay. And the second question is, yeah, in your last slide, I think when you mentioned the varying coefficients, uh, it means that these are coming from varying measures.
They're regularly varying in the sense that as n and over the ratio of n over capital N that you scale with goes to a constant, but both little n and capital N go to infinity. But what I ignored there or didn't discuss is what about when t gets very large too, because that's different. So I'm looking for a very specific case when t is something constant, right? And at the moment t goes to infinity, you get something different happening, that actually the support of the measure splits into two intervals, but that's something we're still investigating.
Thank you. Thank you very much.
Well, it's actually something known, but it's done already by other people for more general cases, but I'm trying to understand it. Let me put it that way.
Okay. Thank you.
Is there any other question? I have one. I have one question. You normally, I'm more or less familiar with these papers, and you normally focus on the asymptotic analysis of the coefficients for the recurrence relation, right? But something that can be probably asked is if can we also analyze the asymptotic of the orthogonal polynomials? I mean, for instance, I'm thinking, for instance, you fix t, and then you compute the asymptotic relative asymptotic of these polynomials for that particular t and the like original polynomials. I'm looking at t as a perturbation, right? Like you're perturbing the measure, and sometimes what people do is to compute relative asymptotics. Is that something that you can? Is that something that you can analyze? Probably.
Yes, definitely. So we did look at that in one of the papers for a scaled polynomial, though. If I remember correctly, it was the one on the sextic case. So m equal to 3.
Yeah.
The sextic Freud weight. So you can have a look in there. We did look at asymptotics for the polynomials in that case.
Okay. I didn't see that one. Okay. And the other question is there a reason, like a physical meaning or something, to introduce that t in that way? Because you put like always, I put it e to the tx square. Is there a reason for that? Because
why it's just that. It's just, I would say it's probably because it's one of the simpler cases, but we're looking at more cases now. So the moment you say you have e to the minus x to the 6 plus tau x to the 4 plus tx squared, we're busy examining that case now. So that has very interesting applications actually in terms of hydrodynamics, etc. And there was some work done on that specific case by various people working in more mathematical physics, thermodynamic limits, etc. So Benassi and Moro is one of the authors that I mentioned. So we are busy working with them, or we've been looking at their work, and we're also planning future collaborations with them. But we're already analyzing one of these cases. But obviously, it gets lots more complicated. And interestingly enough, in that case, when you have the algebraic term in front, so the x to the row, it smooths things. It makes it much simpler. The moment you remove that, the situation in terms of what happens to the recurrence coefficients is much more complicated. And they go through what these mathematical physics people used to say. They follow certain curves, and then they go into what they used to describe as a chaotic behavior, which we can now show that they're also following curves, but it's highly oscillating curves. And then they settle into the asymptotic behavior as n goes to infinity, following one curve. So it's very, very interesting. But at this stage, we're only looking at one of those cases. So the moment you introduce this and you go to x to the 8 and you have 3, you know, x to the 8 plus x to the 6 plus x to the 4 plus x squared. Yes, of course it gets more complicated, but
Yeah.
much more interesting. But not that, so we're trying to analyze one specific case. We're nowhere near doing this for any m
Yeah.
yet.
Okay.
All
Okay.
right.
Thank you. Is there any other question? No? Okay. So thank you, Kerstin. Very interesting talk. Very nice.
Okay.
And thank you, everyone, for attending. So
Thank
the next one, I don't know, is probably in September. We don't have a speaker yet, so if somebody wants to speak, but I'll
I'm
welcome
out.
them. Kerstin is free. Okay, thank you. So let me just finish the recording. Let me see.